All right, welcome to page 3 of lesson 6.3. Now we're working on models, or in other words, word problems. Okay, so our first model, we're dealing with the volume of a rectangular prism. So if the total length here is 16, and then I cut out an x and an x, right? I'm losing an x on each side, so after I make those cuts and fold the sides up, I'll be left with 16 minus 2x. Okay. And then this dimension, the total is 8. But again, I'm going to cut out an x and an x and fold it up. So after I do that, I'll be left with 8 minus 2x. Okay, then my volume, once it's folded up, I'll have, again, a rectangular prism, length times width times height. So my volume will be x times the 8 minus 2x times the 16 minus 2x. All right, that'll equal my volume. And in this case, we want the volume to equal 96. So there's my equation that I need to solve, right? So go ahead and multiply this all out. I don't have a ton of space here, so I worked it out on a separate page, and I get this. Okay. Now I want to set that polynomial equal to 0 and find the zeros. Okay, I'm noticing 4, 48, 128, 96. I could clean this up and have a much easier time if I divide this entire equation by 4. So I'll go ahead and do that. Okay, so I now have a polynomial equation, and I'm trying to find the zeros. If it could factor, I would go that route. I can see I have 4 terms. If I try factor by grouping, this first group I could take out an x squared and I'd have x minus 12. But if I try to make this second group have a factor of x minus 12, it's not going to work out. So this is one of those polynomials where factoring is not going to do it for us. So we're going to have to do our P's and Q's and use our synthetic division. So I'm looking at negative 24. It's nice. We have a 1 right here as our leading coefficient. So I just have to look at the factors of negative 24. So I could have positive negative 1, positive negative 2, positive negative 3, positive negative 4, positive negative 6, positive or negative 8, positive or negative 12, positive or negative 24, right? Those are all my possible rational zeros. That's a lot. And I'm not just going to start and go through them all because we don't want to sit here forever. I've already worked it out, and I found that 2. That 2 goes in there nicely. So I'm going to go ahead and just on a separate paper, since I'm kind of out of room there, go with 2. Okay, so 1x cubed, negative 12x squared, 32x minus 24. 2 times 1 is 2. 2 times negative 10 is negative 20. And 2 times 12 is 24. So you can see 2 is indeed a 0. Okay. And now at this point, I have this depressed polynomial, right? This is x squared minus 10x plus 12. Rather than continuing to guess through here and see if any of them work, right? I'm now down to a quadratic. So since I'm down to a quadratic, I can just check, does it factor, right? If it doesn't factor cleanly, then I know that none of those work. And of course, 12, I could do 1 and 12. That's not going to work. 2 and 6, no, that's not going to work. 3 and 4, also not going to work. So I know it's not going to factor. I know no more of these nice rational choices are going to work. But that doesn't mean there aren't still answers here, right? We can use quadratic formula or completing the square. I used quadratic formula earlier, so I'm going to use completing the square here to refresh your memory on completing the square. Okay, so for completing the square, we want the constant on one side. This is the one time we don't want our equation equal to 0. Then we're going to take half of this b value. Right, so the only way that this guy will be a perfect square is if it's x minus 5 squared. Okay, well, if it's x minus 5 squared, I need 25 right there. And if I add 25 to the left side of my equation, I have to add it to the right side of my equation as well. Okay, so I have the quantity x minus 5 squared equals 13. So go ahead and square root. And I get my 2 roots. Okay, and these are, of course, real roots. So these are valid solutions. Okay, so my solutions are, I'll write it up here, x equals 2, or x equals 5 plus or minus square root of 13. Now, those are real numbers, but I'm noticing an issue, right? 5 plus the square root of 13. Okay, so the square root of 13 plus 5, this is exceeding 8. Okay, so this is going to be too large of a value. This is going to give me something that's got a negative dimension here, okay, which won't work. And same thing, 5 minus the square root of 13, well, that gives me, that says fold a negative amount off of the rectangle, and of course you can't fold a negative amount off of something. So neither one of those answers, even though they are both real roots, neither one is acceptable in context of this problem because they end up with negative lengths of, what is this, cardboard? Oh, wood, yeah, and I can't cut a negative amount of wood off of something. So the only valid solution is 2 inches. Okay. That's the thing about these real world problems or modeling problems. When you're done, you do need to not only say, hey, these are real roots, but also do these real roots provide solutions to the problem. Okay, so moving on. Our next problem is a distance rate time problem. So whenever I come across a distance rate time problem, I like to just set up a quick table. So I have rate times time, and that will always equal my distance traveled. And in this case, I'm talking about 2 people. I have Chuck and I have Dana. Okay. Now, I know that Chuck travels 104 miles, so there's his distance. I know Dana travels 96 miles, so there's her distance. The same time for both, so I'm just going to put T for both of them, their times. And I like capital T, so I don't confuse it for a plus sign. And then the last bit of information, Chuck's rate of travel is 4 miles per hour more than Dana's. So I'll call Dana's rate R, and then Chuck has to be R plus 4, right? Because his is 4 miles per hour faster than Dana's. Okay, now it's rate times time equals distance. So there's my two equations with two unknowns. So I'm going to reorder that. T times the quantity r plus 4 equals 104. And I'm going to have r times t equals 96. Okay. Now solving this, I'll take this bottom equation and solve for either r or t and plug it into the top equation and use substitution to solve. Or I could distribute and then use elimination to solve as well. Either way. How about we do that? That looks easier actually. So I'm going to distribute. So this is going to give me RT plus 4T. Okay. And then I'll subtract the second equation from that. So just like that, I know 4T is 8. So the time traveled for both drivers, 2 hours. Okay, that's not the question being asked though. At what speed does Chuck travel? Well, I now know Chuck's time is 2 hours. So I can take Chuck's equation here. I can put in 2 for T. So 2 times the quantity r plus 4 equals 104. Divide by 2. R plus 4, or in other words, Chuck's rate is going to be 52 miles per hour. So that's Chuck's rate, 52 miles per hour. Dana's rate would, of course, be 52 minus 4, or 48 miles per hour. But they were asking for Chuck's rate, so there's my answer. Okay, moving on. Our next problem is a linear relationship. We have a startup cost or y-intercept of 500, and then a rate of change of $2.50 per calendar, or in other words, a slope of 250. So my function is 2.5x plus 500. Okay. We're going to print 275 calendars, so simply put 275 in there for x. Okay, working that out. We get $1,187.50. All right, moving on. Our next problem is exponential, right? I know that because x is in the exponent. Okay, there's 3 questions here. First, what are the numbers 720,500 and the 1.022 represent in the model? Well, this 720,500, that's the initial or starting amount. So we're talking about an initial time of 1980. So this is the population of Brownville in January of 1980. Okay, so that's the 720. Now, the 1.022, that's the growth rate, right? Anything above 1 means I'm growing. Anything less than 1 means I'm decaying. In this case, it's greater than 1, so I know I'm growing, right? Every year I'm going to multiply the previous year's total with this value that's greater than 1, meaning growth. And the rate would be right there, right? Because if I just multiplied by 1 every year, then I wouldn't be changing at all. So this is how much I'm increasing. So I have a growth rate of 2.2%. Okay, question B. let's predict the population in the year 2000. Well, that's a piece of cake. Just put 2000 in there for X and see what we get. So this is letter B. Oh, I'm sorry, don't put 2000 in there. We should put 20 in there because 2000 is 20 years after 1980. So just put in 20. Okay. Okay, so there's my multiplier. You can see I'm going to grow by a little over 50% in that time. Now we're talking about population. We can't have fractional people, so just round this off to the nearest whole number. So in 2000, we're going to have roughly 1,113,402. Why did I put dollars? This isn't dollars, this is people. Okay, so that's going to be our approximate population in the year 2000 if it continues to grow at that rate. Okay, part C, let's use our model to predict a population of 1 million. So this is an output. So for part C, I have to say an output of 1 million is equal to my model. Okay, so divide by 720,500. Okay, I get that real pleasant decimal there. So I'll just leave it as a fraction. Okay, take the log of both sides. You could use log or natural log. Remember the base, it won't matter. Either will get you the same answer. And you can bring that x down, right? So we get an answer that X, meaning years after 1980, will be equal to the log of 1 million over 720,500 divided by the log of 1.022. Okay, so I still have that in my calculator, so I'm going to go ahead and do the log of that value and then divide it by the log of 1.022. And we can see it's just over 15 years. So that means around 1995, approximately. Okay, that's it for that page.